All right, so as we have said, when you've got an atom, let's say this is the first energy level, we've got an electron here in n is equal to 1, and then you've got n is equal to 2. When you project photons on this electron is going to be able to jump to the next energy level. Now, how much energy do you need for the electron to transition between energy levels? Now notice that for this electron, okay, to go to the next energy level, it needs to what? It needs to gain energy. Now that means the energy that you calculate should be positive. Why? Because you need to gain energy. If an electron is here, it loses energy, it's going to drop. That means if an electron is in the second energy level, it jumps to the first energy level. Just know that the energy is going to be negative. Why? Because energy is lost for that to happen. So even as you get to calculate these questions, you should know, like, it should make sense. Let's say when you've got an electron that is in the first energy level and then it jumps to the third energy level, how much energy is that electron going to gain? We are saying gain because we know that the only way you can jump to a higher energy level is what? When you gain energy. So in this case, the equation will become energy is equal to negative h, then you have got 1 over n final, the final energy level minus the initial energy level, like that. So the energy is going to be this Rayleigh constant you found, negative 2.18 times 10 to the power negative 18. Then we are going to have 1 over the final energy level, as you can see it's going to the third energy level, minus 1 over the first energy level. That's where it's coming from. So this will give us energy being equal to negative 2.18 times 10 to the power negative 18. 1 over 3 square, that is basically 1 over 9, minus 1 over 1, this one. Now 1 over 1 can also be written as 9 over 9. I just want to make the denominators the same. Since the denominators are the same, we can just subtract what is on top. 1 minus 9, that's negative 8 over 9. Alright, so we are going to get the negative 2.18 times 10 to the power 18, we multiply it by the negative 8.9. So I'll say 2.18 times 8 over 9. So this, you can see this is negative, this is also negative, so the answer is going to be positive. So the answer is going to be 1.938 times 10 to the power negative 18 joules. You're able to see that the answer has automatically just come itself positive, meaning that energy has been gained. So this is the energy that is going to be gained for an electron to transition from the first energy level to the third energy level. Now, if it is the other way around, let's say it moves from n is equal to 3 to n is equal to 1. Well, it will be the same energy, but instead of it being gained, it will be lost. Let's try to calculate that. We see if necessary is going to be the same energy, because we saw that energy is quantized. If we're moving from n is equal to 3 now to n is equal to 1, so the same energy is supposed to be seen, but it is either gained or lost. Okay, so in this case, energy is going to be negative 2.18 times 10 to the power negative 18. Then we are going to have 1 over 1 minus 1 over 9. And this will give us energy being equal to negative 2.18 times 10 to the power negative 18. And then 1 over 1, we can also write that as 9 over 9. So since the denominators are the same, we can subtract the powers. That will be 8 over 9. And this will give us, now this is a negative r, so that will be negative 1.93 times 10 to the power negative 18 joules. So that the energy involved either going up or coming down is basically the same. Only what differs is the sign, because it is either lost or gained. In this one, energy is lost, that's why it's negative. In this one, it is gained, that's why the value is also positive. Okay, before we proceed, do we have questions here? Do you have questions here? So an electron that is in the first energy level is called, or is said to be in the ground state. That's called the ground state. Now when an electron goes to a higher energy level, That is called the excited state. Okay, like it's excited because maybe it has gained energy or something like that. So that is it. Are we good with this? All right. Now, we also need to know that as we're able to see an electron like this in different energy levels, there is actually a wavelength. Okay, like the electromagnetic spectrum, if we think of it, like even light itself, light is not just a particle but also a wave. Okay, light is not just a particle but also a wave. Now, what do we mean by light being a wave? Now, something that is a wave should behave like a wave. Like, what are the properties of a wave? So we are saying light is both a wave and a particle. This is actually called the dual nature of light. It acts as both a wave and a particle, and it was brought about by Louis de Broglie. I've seen this question in one of the papers, so you would want to take note. Louis de Broglie. Okay. Now, dual nature means that it behaves the same. If you're talking about something being a wave, that means it has got wavelength, it has got velocity, it has also frequency. All right? It has got wavelength, velocity, and frequency. If something is a particle, you expect it to have mass. So light has got mass. That is why we are saying light is what? A particle. And light has got these properties: wavelength, speed, frequency. That is why we are saying it's a wave. Actually, we know the speed of light. Basically, the speed of all those waves in the electromagnetic spectrum, which is about 3.0 times 10 to the power 8. All right. Now, also electrons have got a specific mass. The mass of an electron, of course, I think it's given in all papers, 9.11 times 10 to the power negative 31 kg. It's going to be given. This is the mass of an electron. Okay. Now, since we are saying light is both a wave and a particle, it should behave the way particles behave, and it should behave the way waves behave. There is one man called Heisenberg. He came up with his principle called Heisenberg's uncertainty principle, which says there is a fundamental limitation to just how precisely we can know both the position and the momentum of an object. That is called Heisenberg's uncertainty principle. We're going to understand it more. There is a fundamental limitation to just how precisely we can know both the momentum and position of a particle. Now think of this: you have got a ball. Think of this, just that same ball you can kick, and then you've got an electron which you barely see. I've put a dot here. Now this dot is even too big. Like an electron is way too small. So if you look at this ball, you know its exact position. Okay, you know its exact. If you think of like a box, if you put this ball in a box, you are going to know its exact position. So that means if I push this ball just a bit, I just push it a bit, like very much small, I'll not necessarily know its speed. So that's why we are saying, if you know Heisenberg's uncertainty principle is saying there is a fundamental limitation to just how precisely you can know both the momentum and the position of a particle. Okay? Because of this, if I know the position of an object, it is very difficult for me to be able to know what its speed or its momentum. Remember, speed is just mass in motion. I mean, momentum is just mass in motion. Momentum is mass times velocity. So for this one, I'll fail to know its momentum if I push it just a bit, because I know exactly its position. But for an electron, if I put it in the same box, I will not be able to tell its position. For example, like this is a 1 centimeter box. How do I just know like 1 centimeter exactly? Okay, if this is 1 centimeter now, just the position where this electron is, how will I know? It will be very difficult. So I don't know necessarily the position of this electron. That will make me to know if I just push it a bit, it will be able to move, and I'm going to know its momentum because I'll know its speed at least because I'm able to see it move. Now, if I push this one just a bit, I'll not be able to see it make any movement that is not negligible. So I don't know necessarily its position, but I know its speed. This one I know necessarily its speed, but I don't know. I mean, I know necessarily its position, but I don't know its speed. That's called Heisenberg's uncertainty principle. Meaning that if you know more about the position of something, you are going to know less about its speed. If you know more about its speed, you are going to know less about its momentum. Okay, so Heisenberg's uncertainty principle has got the equation change in position multiplied by change in momentum should be greater than or equal to, we've got this symbol divided by 2. Now this same symbol that we've put here has got a value. Okay, this symbol has got a value. This symbol actually is also equal to h over 2 pi. This h you are seeing, we're going to use it a lot of times from this time on. That is called Planck's constant. So the change in position multiplied by the change in momentum is always greater than or equal to Planck's constant divided by 4 pi. If we substitute where there is this value, substitute with this. This is the equation that we're going to get. So this is called Heisenberg's uncertainty principle. Now Planck's constant is a known value, 6.626 times 10 to the power, that should be zeta negative 34. We are going, it's actually given when you've been given such a question, and we know pi is a constant. So if you know the position, you should be able to determine the momentum of something. Now since position times momentum should always give you a value which is greater than or equal to this constant, like this side we have got a constant. As I've said, Planck's constant, this is a constant, pi is a constant, meaning that if this value is big, this one should be small because we always want to get this value. That is why if you know the position of an object, you will not be able to know more about its position. Let me just pause a bit and see if we are okay. Do you have any question? Any question? Okay. So now think of this. You have got this object which is here. Okay, it has got a big mass. For example, maybe this object I've put here, let's say has got a mass of, can I say 0.5 kg? Okay, this one, the mass is 0.5 kg. This one, its mass, we know this is an electron, 9.11 times 10 to the power negative 31 kg. Now let's say these two objects are both from the Heisenberg's uncertainty principle, change in x times change in momentum is greater than or equal to Planck's constant over 4 pi. Let's say both of these objects are moving, let's say they're at a position, can I say their change in position, okay, like it was at the initial position, now you just push it a bit, like just think of pushing this a bit such that maybe if it was at 2 centimeters it goes at 2.01, so the change in position is 0.1. Let me use meters so that you just be good working with this. Okay, 0.1 meters. Even this one we move it for 0.1 meters. Now let's determine the change in speed for these objects. Let's determine the change in momentum, let's say. Okay, now let's start with the mass which we have here, the ball. So the change in position we've been given as 0.1 meters. Okay, 0.1 meters, and then multiply by the change in momentum. that should be greater than or equal to Planck's constant is a constant value is 6.626 times 10 to the power negative 34. It is given in joule second, that's a unit, joule second, and then divided by 4 pi. We know pi is a constant. Now I want to remain with change in momentum, so we'll divide also both sides by what? By 0 0.1. So we'll divide by 0 0.1 this side, also this side will divide by 0 0.1 such that this cancels with this. Now let's determine the change in momentum. Change in momentum is going to be equal to, we are going to multiply. Okay, first we have got 6.626 times 10 to the power negative 34. And then we are going to divide the whole of this value. Divided by, we have got 4 multiplied by pi, and then multiplied by 0 0.1. So this one has given me a change in momentum of 527.28 times 10 to the power negative 36. Now, momentum is mass in motion. Mass times velocity. We know mass is given in kg, velocity is in meters per second. So this is the momentum of the particle. Now, what are the momentum of an electron? Change in momentum is going to be greater than or equal to Planck's constant, 6.626 times 10 to the power negative 34, divided by 4 pi times the position, okay, times the position, which is 0 0.1. So basically, even in this one, the change in momentum is going to be the same value, which is 527.28 times 10 to the power negative 34 kg meter per second. Now let's determine their velocities. We know that momentum is mass times velocity. The momentum of this one, that means that the velocity is going to be momentum over mass. So the momentum is 527.28 times 10 to the power negative 34. For the ball, the mass is 0.5. So divide by 0.5. Okay, let's see what we get. Divided by 0.5, that is going to give us 1054.56 times 10 to the power negative 36. This is going to be in meters per second. Let's find for an electron the velocity also change in momentum, which is also 527 times, that is a 0.28 times 10 to the power negative 36. Now divided by the mass. The mass of an electron, 9.11 times 10 to the power negative 31. Let's determine its velocity. Okay, divided by 9.11 times 10 to the power negative 31. So this has given me a velocity of 0.579 meters per second. Now you can see like 0.579 is way too big as compared to this number that is raised to a negative 36, which is very small. So you've seen we never knew the exact position of this one because it is very very small, okay? Like we will not know the exact position of this object, but we necessarily know the position of this one because it's very big. So you see that there is a significant difference. All right, so that is Heisenberg's uncertainty principle. There is a fundamental limitation to just how precisely you are able to know both the position and the momentum of an object. So if you know the position of an object, you'll not be able to know how fast it will be able to move if you pause it just for a bit, because the movement will be manageable. Okay,